Hello, everyone. I am glad to present our work, NeRAG, Neuro-Explicit Retrieval Augmented Generation for Real-Time Interaction in Digital Humans. Real-time gesture generation is a key challenge for building digital humans. When we talk to a digital human, it needs to respond with natural body language. But today's methods face a trade-off. On one hand, deep generative models like diffusion can produce diverse gestures. But they are slow, each gesture takes seconds. On the other hand, retrieval-based methods are fast, but they lack semantic diversity and cannot adapt to changing contexts. Can we combine the best of both? This is the goal of NeRAG. This is the overall system of NeRAG. Our core idea is simple: split the task into a brain and a body. On the left are the inputs. The system takes C, the speech, audio and text, and S, the kinematic state like joint positions and velocities. These go into the module on top, Phi, the neural motion planner. This is a transformer-based brain. It predicts a latent motion query, a signal that captures the semantic intent for the next gesture. This query goes to the lower right module. Psi, the explicit motion executor. This is a graph-based retrieval body. It searches a pre-built atomic action graph G and picks the best matching motion. The system outputs S, the final motion to drive the digital human. The key innovation is the recurrent motion state feedback, RMSF, on the left. Notice the loop from output back to the planner. We do not feed back the planner's own guess. Instead, we feed back the real executed motion. This creates a closed-loop system. The planner can now feel the current pose, which greatly reduces jitter and drift. Now let us look at how the atomic action graph is built. Each gray dot is an atomic action, not a single frame, but a short motion clip that represents one complete gesture, like a nod or a wave. Each clip lasts about 1 to 3 seconds. Actions in the same cluster have similar meaning. This is semantic partitioning. We extract text descriptions for each action, turn them into vectors, and run k-means to get clusters. This reduces the search complexity, making retrieval much faster. We group atomic actions based on their text descriptions. Each action has a text label, for example, nodding in agreement or waving to refuse. We use TF-IDF to turn these texts into feature vectors and cluster them. Each cluster is indexed by a semantic anchor. For example, agreement, refusal, and metaphoric. The planner predicts a query Q, a semantic vector. By computing its cosine similarity with each anchor, we quickly find the right cluster. This prunes about 95% of irrelevant nodes. We now have several clusters. Any two clusters can connect directly. Each edge is a motion transition through smooth blending. We define a cost function that measures pose and velocity differences at the boundary. An edge exists only if this cost is below a threshold. This guarantees smooth motion along any path. We see a directed graph. Each node is an atomic action. Arrows show possible transitions. Not every pair is connected, edges have conditions. The text says, a directed edge exists only if the transition is physically smooth. The red edges mark these valid transitions. This ensures the output is a continuous, natural motion stream, not a random sequence. This is the key difference from naive frame-level search. A node is highlighted by a blue circle. This is the selected atomic action. Pink edges mark the path the system took to find it. The text on the right says, this topology ensures that any path in the graph results in artifact-free motion. This comes from our hierarchical graph-constrained search with 2 stages. This achieves retrieval in under 2 milliseconds, with 150 milliseconds end-to-end latency and 120 FPS throughput, while under the real-time threshold. We are going to show the rendered animation of NeRAG and a comparison between NeRAG and baseline models.
One time, my friends and I dared each other to go to a place that we believed was haunted. Near my house, there was a creek that we were told bad things had happened there. So we decided to go at midnight and try, which, if you believe in that sort of thing, allows you to speak to the dead. We decided to turn on the CTR TV, which is the older TV in our house that still had a tube in it, and to put on white noise. So we flipped it onto a channel with white snow. When I was in university almost more than 10 years ago, the community security was not very good, and we are more often than not in dangerous situations.
Whale songs are like, and not many people know this about whale songs, but I saw this documentary about whale songs, and like there's like genres of like whale music and songs. So they're like, a whale song can be like country and like I think the worst food that would be liquefied and drank through a straw would be something meaty, because I don't think that would liquefy well. Like I can't imagine drinking a steak, but maybe I'll feel about it differently when I'm old.
This is a demonstration of NeRAG running on Unreal Engine. It's now driving a metahuman. We use in the wild audio from TED Talk to test the model's generalization.
At this point, most people really only care about the television show. I know this from experience. Okay, so the show was NBC's Saved by the Bell, the new class. Right is truth, right? Well, that's what I thought. Then, from age 12 to 25, my retinas progressively deteriorated. My sight became
For objective evaluation, we selected 4 standard metrics to cover different aspects of gesture quality. FGD, or fresh gesture distance, measures the distribution gap between generated and real motions. A lower FGD means the output is closer to natural human gestures in the feature space. L1 diversity measures how varied the generated gestures are across frames. Higher diversity suggests the model avoids repetitive motion patterns. Beat consistency evaluates how well the gesture rhythm aligns with the speech beat. This is important for co-speech gesture, where gestures should synchronize with the audio. AITS, or average inference time per step, measures the system's latency. This is critical for real-time interaction. We want this as low as possible. We evaluated all methods on the beat dataset under identical settings. We also conducted ablation studies by removing key components. The motion graph, the spatiotemporal attention, and the feedback mechanism to measure each part's contribution. All ablations stayed within the retrieval-based paradigm, so the performance changes reflect the specific design choices, not a switch in methodology. Finally, we ran the same evaluation on the ZEGGS dataset to test cross-dataset generalization and confirm our results hold across different data sources. To sum up, NeRAG delivers real-time performance with high motion quality. On the beat dataset, NeRAG achieves the best FGD and shortest inference latency, significantly outperforming existing methods. We also evaluated on the ZEGGS dataset to test cross-dataset generalization. NeRAG again achieves the best subjective scores along with the best FGD and the fastest inference speed. We also ran a user study to evaluate how natural our gestures look to real people. We invited 30 volunteers to watch short video clips of different gesture outputs. They rated each video on 3 metrics: human likeness, does it look like a real person? Appropriateness, does the gesture match the speech? Style appropriateness, does the style feel consistent? We also conducted pairwise t-tests on all subjective metrics. The results confirm that NeRAG's advantages over all baselines are statistically significant.